Hello, my name is Andrew Rush, and this is my Physics 2212 Lab 5 over magnetic braking. Introduction. So the purpose of this lab was to observe and evaluate how a magnet falls slower when dropped through an electrically conductive tube. We observed what happens in the real world and then modeled the interaction in GlowScript. The results was that the average falling time was about 1.36 seconds, but the model's predicted falling time was 1.065 seconds. Some fundamental principles used is the Biot-Savart law, Faraday's law, Ohm's law, Lenz's law, and Newton's law. In the third law that says every force has an equal and opposite reaction force. The experiment itself, so the physical properties, the tube length was about 0.3 meters, the foil width was about 0.05 meters, tube's inner radius was about 0.027 meters, and the magnet mass was 0.023 kilograms, and the magnet mu value was 5.853. And the system is the bar magnet and tube, and the surroundings is everything else. And over here is the experiment. The experimental results, so the first trial was about 1.35 seconds. Next was all the same. Next was 1.3. After that was 1.45. And finally, it was on the last trial was 1.36 seconds. So coming out to an average time of 1.36 seconds. Some code. Here we have our physical constants being declared, the properties of the magnet, and then we created a function to calculate the magnetic field of the bar magnet. Then we created a function to calculate the magnetic flux. Then we calculated the current in the ring. Then we computed the typical B field at each ring. Then we calculated the gravitational force on the magnet and then the net force on the magnet. After that, we updated the magnet's velocity and position. And the results of this, as you can see over here, is the graph of time, and then the actual experiment itself and the code. Some assumptions is that the only forces are from the magnetic field and gravity, and the dipole moment is always aligned with the axis of the tube. Magnet doesn't tumble. Some sources of error could be inaccurate magnet timing or some friction between the magnet and walls of the tube, and inaccuracies from previous assumptions. As you can see down here in the results, the model predicted 1.065, which deviates from ours by about like 0.5 or so. Some discussion. Which color corresponds to clockwise current as viewed from above, and which is counterclockwise? Red indicates clockwise, and blue indicates counterclockwise. These currents are induced to create a magnetic field which resists the change in flux through the ring. So what happens to the dynamics of the system when you flip the magnet around? The motion of the magnet wouldn't change, but the currents would be flipped. And how does the total time in tube of your real world system compare to that of your computational system, and how might it be made more accurate? The model computes a faster time. Both methods could be made more accurate by improving real-world data collection methods and accounting for air resistance and friction in the model. So what is the shape of the velocity versus time plot? Tell you about the forces acting on the bar magnet. On the ends, gravity is the strongest force. In the middle, gravity and force from the magnetism are equal. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? By Ohm's law, decreasing the resistivity would decrease the resistance, would increase the current flowing through the tube. By Lenz's law, increasing the current would increase the force exerted on the magnet, causing it to fall slower. What if holes or slots were cut into the tube? How would this affect the ring current in your model? A cross-section of the tube that contains a slot would be analogous to an open circuit, meaning no current would flow through this section. This means no magnetic field would be induced, causing the magnet to fall faster. So that is all that I have for this lab. Thank you so much for watching.